In this video I'm going to go through the 2022 paper, and this is for Unit 1 higher tier. Question 1 part A. I have to use only the elements in the table above. So name an element that forms an oxide which is a colourless liquid at room temperature. Well, I'm going to go through some examples first. So if you have these ones reacting with oxygen, you form a metal oxide. They will be solids because they will be ionic substances which have high melting points. So it's not going to be these ones. If carbon reacts with oxygen, it'll give carbon dioxide. That's a gas. Oxygen, okay, well that's just going to be oxygen. And these don't react to noble gases. They've got a full outer shell of electrons, which makes them stable. So it's going to be hydrogen, because when hydrogen reacts with oxygen, it produces water. And again, I'm careful here to give the name, not the symbol. Part 2, one of the elements forms an oxide which is a colourless gas at room temperature. I've already gone through this. When carbon reacts with oxygen, it forms carbon dioxide. That's a colourless gas. And I have to write the formula. So that will be CO2. I suppose you could also write CO, carbon monoxide. Write the formula of an ionic compound formed between two of the elements. An ionic compound is formed from a metal and a non-metal reacting together. So I could pick any of these ones, combining with, say, oxygen or hydrogen. So I'm just going to pick sodium and oxygen. And I have to write the formula. There's going to be Na2O. But just as an example, I could also have done, let's say, K2O. And I'll do one more. I could also have had, let's say, I'll do zinc hydride this time just to do something a bit different. Zinc has a valency of 2. Hydrogen has a valency of 1. So that's the formula of zinc hydride. Part B has to do with the reaction of the alkali metals with water. Now, I'm already told that the potassium floats, moves, melts, burns with a flame, and then it disappears, or don't say dissolves. A colour solution is formed. So, what safety precautions would be taken apart from wearing safety glasses? Well, this is a very vigorous reaction. So I would want to make sure that a small piece of metal is used. I could also use tweezers so that I'm not handling it. I could also use a large volume of water. That would allow the heat that's generated in the reaction to dissipate more. Use a safety screen, remove oil from the metal, stand well back. So any two of those answers would do. Potassium floats in water because it is less dense than water. Part 3, why does the potassium melt during the reaction? Well, there's so much heat generated, it causes the solid metal to melt. Part 4, potassium burns with a lilac flame. And then part 5, in terms of electrons, why is the reaction of sodium with water less vigorous than the reaction of potassium with water? Well, if you imagine that a sodium atom will look like this, with one electron on the outer shell, obviously there would be inner electrons, but I'm not drawing those. And if I then draw a potassium atom, which is below sodium, so it's 2, 8, 8, 1. You can see that the outer electron in potassium is further from the nucleus compared to sodium. Here it's much closer. So it's going to be attracted more to the nucleus in sodium than it would be in potassium. So that means it's more difficult to remove the outer electron in sodium than it is to remove the outer electron in potassium. Now, I could have given this answer in terms of the potassium. So I could have said in potassium the outer electron is further from the nucleus, is less attracted to the nucleus, and so was easier to lose. So there's the definition of isotopes, and started off with atoms, or atoms of the same element, which don't just go straight into the answer with same number. Also, don't say an atom, but you need at least two of them. For part 2, you have to work out the relative atomic mass. So for this, I look at the table and see that these are percentage abundances, not relative abundances. So what I would do is take the isotope of neon 20 and multiply that by 90.1. And then I'm going to add on the total mass of the neon 21. So 0.3% is neon 21. And then I'll add on the total amount, if you like, or the total number of the neon 22 isotopes. So that's the isotope 22, and 9.6 of all of the neon is neon 22. So now I'll add all of that up. That will give me the total mass for 100 atoms, because we're dealing with percentages here. But I want the mass for one atom. So I have to divide this by 100, and I get an answer of 20.2. Note that it says to give your answer to one decimal place. Part 3. So I'm told the radius of a neon atom is 45,000 times larger than the radius of the nucleus. And I'm trying to calculate the atomic radius. Okay. Well, if the nuclear radius is 3.5 or 3.50 times 10 to the minus 15, then the atomic radius will be the nuclear radius times 45,000. Remember, the question has told me that the radius of an atom is 45,000 times larger than the radius of the nucleus. So that's why I'm multiplying these two together. And that gives an answer of 1.58 times 10 to the minus 10 meters. Now I've got to convert this to nanometers. So I'm just going to draw out this table, and I'm converting from meters to a nanometer. So in here, I want to put how many meters go into a nanometer, because I'm going from meters to nanometers. Now I've already been given this information here, and you can see it's 1 times 10 to the minus 9 meters. So I'm going to put it in here. And then what I do is simply divide the top by the bottom. The units will cancel out, and that then will convert this into nanometers. So 1.58 times 10 to the minus 10 divided by 10 to the minus 9, and that works out to be 0.158. Part B is a very standard type of question at GCSE. So you have to fill in this table. The thing that you really need to be careful of is to remember that the table contains atoms and ions. So sometimes people just think these are all atoms. So with that in mind, I'm going to go ahead and complete this table. hydrogen, the first one here has an atomic number of 1. That's what makes it hydrogen. So it has to be one. If it's not 1, it's not hydrogen. So now I'll move on to mass number. Now it might be tempting to go to the periodic table where you would see that the hydrogen has a mass number of 1. So why is it not 1 here? Well, the mass number is the number of protons plus the neutrons. And you can see from the table that this particular atom has 1 neutron and 1 proton. That means that the mass number for this hydrogen atom is 2. So it's obviously an isotope. So again, just be really careful and pay attention to the protons, the neutrons, electrons if they're present, or the electronic configuration as we'll see as we go through the table. Next one then is K+, that's an ion. Atomic number 19, that identifies it as being based on potassium. The number of neutrons, well, mass number minus atomic number equals the number of neutrons. So this is going to be 20. It's just 39 minus 19. The number of protons, well, the atomic number is the number of protons. That's the definition of atomic number. So that's going to be 19. Again, you need to be careful here that you don't just think, okay, 19 protons, there'd be 19 electrons. In an atom of potassium, there would be 19 electrons. Atoms are neutral overall. But we're told here that this is K+. That means there must be more protons than electrons, and it's 1+. So there's 1 extra positive charge. There must be 18 electrons in this, so that would give a 1+ charge. The electron configuration therefore would be 2, 8, 8. Third one, atomic number 13. Look up the periodic table, that identifies the element. You'll see that that is going to be aluminium. Now at this stage I don't know if it's charged or if it's neutral, so we'll need to come back and check that. The mass number, well, the mass number is the number of protons plus neutrons. I've got neutrons, 14. The protons, atomic number is the number of protons, so that's going to be 13. That'll give 27. Now the electron configuration is 2, 8. If this had been an atom, it would have been 2, 8, 3. So 13 electrons, 13 protons, they would have cancelled out and made the atom neutral. But this is 2, 8, so that gives 10 electrons, but there are 13 protons. That means that there are 3 extra positive charges. So going back to this side, it's not an aluminium atom, it has to be an aluminium ion, and it's going to be 3 plus or plus 3. The fourth one, number of protons 17, so I can fill in atomic number. Atomic number equals the number of protons, just always. I can then look up the periodic table and identify the element that has an atomic number of 17. That's chlorine. Again, I need to go through some of the rest of this before I can determine if it's neutral or charged. Mass number is the neutrons plus the protons. That's going to be 37. Don't put in 37.5. And you must use this table to work out the mass number. Electron configuration 287, got 17. Well, there are 17 protons. These are the same, therefore this is an atom, so I can just leave it as Cl. Final one, oxygen has an atomic number of 8, and that is obviously the same as the number of protons. The neutrons then, is worked out by subtracting the atomic number from the mass number. This is going to be 10. This is an isotope because in the periodic table the mass number of oxygen is 16. This is 18, so it's obviously an isotope. Electron configuration. Again, don't be tempted just to write down 2, 6. So it's the same as the protons because it's 2 minus. An oxygen atom would be 2, 6. But because this is 2 minus, it means it has gained an extra 2 electrons. Therefore, this is going to be 2, 8. Question 3. Name substances A, B, and C. Okay, so let's look at A. Here we've got an acid plus an alkali, gives us salt plus water. Well, the surname part of the salt, if you like, always comes from the acid. There's going to be a chloride, and the first part is usually a metal. So here we've got potassium. So substance A is going to be potassium chloride. Remember, a salt is an acid in which the hydrogen ions are replaced with metal ions or ammonium ions. Equation 2, this time we're making copper nitrate. The nitrate tells us that the acid used is nitric acid. So the first part has to be copper. Now copper doesn't react with acid, so we just can't add copper to acid to give copper to nitrate. It has to be copper something. Now the clue here is carbon dioxide, and that indicates that the original substance, substance B, was a carbonate, because carbon dioxide is always produced when carbonates react. So substance B has to be copper 2 carbonate, and make sure you put in the 2 there after the copper. Equation 3, zinc oxide, that's a base. The acid here is based on this part of the salt, because this is the salt, and sulfates are formed from sulfuric acid. Part 2, copper 2 nitrate. I'll write the formula for each part. The nitrate is a valency of 1. Well, I don't need to put that after the copper. Copper 2, that's the valency of it, has a valency of 2. I put it after the nitrate. Because the nitrate is made up of different elements, that has to go inside brackets. So CuNO3 brackets 2. Don't include any charges. Part 3, hydrated, just means it contains water of crystallization. B part 1 is about making crystals, pure dry crystals of hydrated calcium chloride. Now this type of question is fairly common, and it's common in this format. We have to give an extended answer. So we're told that it's going to be prepared from solid sodium carbonate and hydrochloric acid. I'm going to need something to put the acid in, which is usually a beaker. Sometimes the quantity of acid is required. If so, I would go for around 25 or 30 cubic centimetres of acid. Next thing I would do is add the carbonate to it. So how do I know when to stop adding it? Well, when the carbonate reacts with an acid, gas is given off, carbon dioxide gas is given off, there would be fizzing. So I know when to stop adding the carbonate as the fizzing will stop, or no more gas would be given off. This means that there would be excess calcium carbonate left in the beaker. It just would be lying there, which has to be gotten rid of. So the next step would be to filter. That would now leave me with a nice solution of calcium chloride. So the calcium chloride is in the water. In order to get crystals out of that solution, I have to evaporate off some of that water, and usually evaporate off about a half of the volume. This actually decreases the solubility of the crystals, so it means they're more likely to appear. Then the solution needs to be left to cool and crystallize slowly. And the reason we leave it to cool and not just continue to heat it, because we want hydrated calcium carbonate. If this is heated too strongly, the water of crystallization would be driven out of the crystals. So you wouldn't end up with hydrated salt. It would just be an anhydrous salt. Sometimes then, when the crystals have formed, there's still some liquid left. So the next step could be to filter off the crystals. Now at this stage, the crystals can still be quite damp, so they need to be dried between pieces of filter paper. We're going to say dry between 2 pieces of filter paper. Just don't say dry between a piece. You must indicate that there's more than one there. You could also use a desiccator or a low temperature oven, but the oven would have to be a low temperature, because if it was too high, then it could actually drive out the water of crystallization. So you wouldn't get crystals, you just get an anhydrous salt formed. So if you've got 6 or 7 of those points, you get the 6 marks. If you get 4 or 5 of those points, you get 4 marks. In a balanced summary equation, calcium carbonate is CaCO3. Hydrochloric acid is just HCl. That will form calcium chloride. Calcium is a valency of 2. Chlorine's 1, so you swap them over. Plus water plus carbon dioxide. And you can see here that there are 2 chlorines on the right, only one on the left. Put it in front of the HCl, and that balances the chlorines. It also balances the hydrogens too. Okay, we're going to now draw the bonding in magnesium chloride. Now the question does tell us that it's an ionic compound, but you should realise that anyway, because this is a metal, this is a non-metal, and when a metal and non-metal combine, it forms an ionic compound. Now for ionic bonds, you have to show the atoms at the start, and then you show the ions that they go to. So draw out magnesium and chlorine atoms to start with. Now the formula for magnesium chloride is MgCl2. So we're going to need 1 magnesium and 2 chlorine atoms. So I've drawn them out. Now you don't have to draw the magnesium in the centre with the chlorines either side of it. That's not important. So the magnesium will lose the electrons, and the electrons go from the metal to the non-metals. So one of these electrons will go over and pair with this electron, and the other one will go and pair with this electron. So now I will show the ions formed. So there are the ions, and we'll have to include the charges. It does tell us to include the charges, but you would always include the charges anyway, even if you weren't told. So the magnesium then becomes Mg2+. Sometimes you'd see it with square brackets and a 2+ outside it. Either way is fine. And then the chlorine atoms become chloride ions. Well, they've gained a negative charge, so that means it would be Cl-, and the same thing is going to apply to the other one. An ionic bond is the attraction between oppositely charged ions. Part B. Let's see now. I have to do chlorine molecule, the total number of electrons in covalent bonds in one molecule. Well, chlorine is Cl2. This line represents a covalent bond, which is the sharing of a pair of electrons. So there'd be 2 electrons here in one molecule. And then the number of lone pairs in one molecule, well, each of the chlorine atoms has 7 electrons in this outer shell. So if I just try and draw them in here, like that, so you can see this chlorine has 1, 2, 3, 4, 5, 6, 7 originally. This chlorine will have the same number. Already got 1, and 2, 3, 4, 5, 6, 7. how many lone pairs. So those are pairs of electrons which are not involved in a bond. Okay, if we look here, there's one lone pair, 2, 3, 4, 5, 6. And nitrogen, well, nitrogen has a triple covalent bond. I'll just draw it out using a dot and cross diagram. Each of these is a nitrogen atom. Nitrogen has 5 electrons in its outer shell, and the thing about nitrogen is that it contains a triple covalent bond. You need to remember that. So that's 1 covalent bond, 2, 3. Now if we look at the axis first of all, that'll represent the electrons in this atom. Remember, nitrogen has 5 electrons in the outer shell, so I've got 1, 2, 3. I need another 2. 1, 2. And then the same sort of thing is going to apply to the other one. I've got 1, 2, 3. I need 4 and 5. So the first part of the question is, what is the total number of electrons in a molecule? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there are 10 in the outer shells. However, the question does state in one molecule, so it's not asking about the number of electrons in the outer shells. So don't forget that nitrogen is 2, 5 originally. There would be an inner shell of electrons in both of them with 2 electrons each. So that means the total number of electrons would be 14. The total number of electrons in a covalent bond, well, you can see here there are 6. The next part, the number of lone pairs, 2, because there's got 1 there and 1 there. And then ammonia, again I'm going to draw it out because that will help. These are hydrogen atoms. This is the nitrogen. So nitrogen has 5 electrons in the outer shell. Each hydrogen has 1 electron. It'll pair up with the nitrogen electrons. And I said that nitrogen has 5 in the outer shell, so I still need to draw in another couple of electrons there. So the total number of electrons in one molecule, well, just looking at the outer shell, that'll be 2, 4, 6, 8. But again, remember, the question is not asking about the total number in the outer shell, it's in one molecule. So this nitrogen will have an inner shell with 2 electrons. So that's why there'd be 10. Then the number of lone pairs, well, there's just, you can see 1. Suggest a formula for nitrogen trichloride. Well, the tri there means that there are 3 chlorines. Nitrogen trichloride. Why is nitrogen a gas? Now, nitrogen is a simple covalent molecule. And all simple covalent molecules have low melting and boiling points, and the reason is the same. It does not matter if it's nitrogen, oxygen, carbon dioxide, ammonia, etc. You give the same answer, which is there are weak van der Waals forces between molecules which require little energy to break. Part C then, this time we're going to be showing covalent bonds. As methane in water contains non-metal elements, and when non-metals combine it forms covalent compounds. And methane is CH4, so I'm going to draw a carbon and then 4 hydrogens around it. Now when you're drawing dot and cross diagrams for covalent compounds, you only need to show the outer shell electrons. So I'm not going to show the inner shell here, there would be 2 electrons in there. So carbon has 4 electrons in its outer shell. 1, 2, 3, 4, and these are all single bonds. Each hydrogen has 1 electron. That's the bonding in methane. Water, which is H2O, so there's 1 oxygen and then 2 hydrogens. Oxygen has 6 in the outer shell. Again, there would be 2 electrons in the inner shell, but I'm not going to draw those. So those electrons will pair up with an electron from each hydrogen. So that's 2 used up already. I said there were 6 in the outer shell, so 1, 2, 3, 4, 5, 6. And then each hydrogen has an electron. There's the bonding in water. Question 5 requires a definition of alloy. So an alloy is a mixture of elements, at least one of which is a metal. Don't just say it's a mixture of metals. Okay, so it can be metals and non-metals, but at least one of the elements has to be a metal. Now for this particular answer there were 3 marks. So a third mark was going for you saying that the resulting mixture has metallic properties. So think of brass and bronze. They still conduct electricity, they're malleable, etc. Part 2. Why is the alloy harder than nickel? Well, if you think of the structure of metals, now I know there are positive ions, they're delocalized electrons, but if I just draw these circles to represent the ions or the atoms, when you're answering this type of question, you can refer to the atoms. So these atoms or ions would slide over each other. But in an alloy, there are different sized atoms. So I'll draw just a filled circle to represent the different size. So now, if I try to bend this by pushing this layer over the second layer, you can see, hopefully, that this atom in here sort of blocks the top layer from sliding over. Likewise, this atom here would block this second layer from sliding over. And so you just convey that in your answer. Part 3 then is about a flame test. Now remember, for a flame test you need nichrome wire, which you would dip in concentrated hydrochloric acid into the sample and then into blue Bunsen flame. So if you get a brick red colour, that means that the ion is calcium. It is important to say it's a calcium ion, not just calcium. If lithium ions are present, then it will be crimson, and yellow-orange indicates that sodium ions are present. Part B then is testing for ions, and a precipitate is just a solid that's formed on mixing 2 solutions. Now in reaction 1, the precipitate that's formed is barium sulfate. That's a solid and it is white. And this is a test for sulfate ions. So when you add a barium chloride solution, that's where these barium ions are coming from. Okay, so they're coming from barium chloride solution. So anytime you add this solution to a solution containing sulfate ions, you'll get a white precipitate, which indicates that the sulfate ions are present. In reaction 2, well, when you add sodium hydroxide solution to a solution containing iron 3, and we know this iron 3 because there's a 3 here. That has come from the iron originally. This is the solid precipitate, iron 3 hydroxide, and it is brown. So say this is the precipitate, which is brown. Now sometimes you're asked to write reaction 2 as an ionic equation. So that's just looking at the ions of interest to us. Well, this, the iron 3 hydroxide, is the solid that's formed. So we want to show how that solid is formed. Well, it comes from iron 3, which is dissolved in the solution, so it's aqueous, and it also contains hydroxide ions. And there are 3 of them. This equation has to balance. Now, the hydroxide ions are also in solution, so I have to put aqueous in front of that. So that's the ionic equation for reaction 2. Reaction 3, the solid is the silver iodide, and it is yellow. Reaction 3 is often asked as an ionic equation also. So what you would have to do is show how the solid, the precipitate of silver iodide, is formed from its ions. So it would be Ag plus, aqueous, because they're dissolved initially. So these silver ions come from the silver nitrate solution. Silver nitrate solution, when you see that, you should automatically be thinking, okay, I'm testing for a chloride, bromide, or iodide. And they are going to react with iodide ions. And those have come from the potassium iodide solution. And when they combine, it forms the insoluble silver iodide. It's a solid, and that's what the yellow precipitate is. Okay, on to part 3. Rewrite equation 1 to include state symbols. The barium ions are dissolved initially, as are the sulfate ions, and the barium sulfate is the precipitate, so that's the solid. Reaction 2, well, I've already done it up above, so I'm showing the iron 3 ions reacting with hydroxide ions to form the brown precipitate of iron 3 hydroxide. Now it needs to be balanced. You can see here that I've got 3 hydroxides, so I need to put a 3 in front of that. Now you might be thinking, okay, what about the symbols or the state symbols? Well, if the question doesn't ask you for them, you don't have to put them in. You see in this question, part 3, it does state that state symbols have to be included, whereas here it doesn't mention it. So I would just leave them out. And the precipitate in reaction 3 is silver iodide. On to question 6 then. So A, part 1, have to calculate the number of moles of chromium 3 oxide in 1.9 kilograms. Now remember, when you're working out moles, the mass has to be in grams. So I've got to convert the 1.9 kilograms to grams. I do that by multiplying by 1,000. So it's 1900 grams divided by the MR, or the RFM, of chromium 3 oxide. So this is chromium 3 oxide. So you work out that RFM, and that is 152. So that works out to be 12.5 moles. Part 2, calculate the number of moles of magnesium in 1.2 kilograms. So again, it's in kilograms, which means we'll have to convert that to grams by multiplying by 1,000. Divide that by the RFM of magnesium, which is 24, and that's 50. So which reactant is limiting? I'm going to put the number of moles that I've worked out underneath each reactant, just to make it easier. And let's say I take the magnesium one. So if I've got 50 moles of magnesium and it reacts in a 3:1 ratio, that means starting off with 50 moles of magnesium, I would need 16.7 moles, say, of the chromium 3 oxide, because it's, as I said, it's a 3:1 ratio. Now I don't have 16.7, I've only got 12.5, so I don't have enough. That means that the chromium 3 oxide is limiting. I'll do it the other way. So let's get rid of this. If there are 12.5 grams of the chromium 3 oxide, and it's a 1:3 ratio, that means that we will need 37.5 moles, or at least 37.5 moles. Well, we've got 50, so we've got more than we need. So that tells us the magnesium is in excess. So the answer then here is the chromium 3 oxide. You can give the symbol or the name. The question just says state. Part 4, then we have to calculate the mass of chromium formed. So I've included the equation here so you don't have to flick back to see what it is. And from the previous questions, I've worked out that the number of moles of chromium 3 oxide is 12.5. I'm trying to work out the mass of chromium formed. So you can see it's a 1:2 ratio. Therefore, it's going to be 12.5 times 2, which equals 25. So that's how many moles of the chromium will be formed. Then I've got to convert that to a mass. So 25 times the RFM, the MR of the chromium, which is 52. And that works out to be 1,300 grams. Part B. Now there's a water crystallization question. We can tell that because here's the equation and there's a dot between these two parts. So I have to work out the value of X here. Now to do this, we need to work out the mass of the anhydrous chromium 3 nitrate and the mass of the water. Okay, so let's start with the chromium 3 nitrate. Well, we're told that 5.95 grams of anhydrous calcium 3 nitrate remained. So that's it after the water of crystallization has been removed. So that is straightforward enough. The mass is in grams. Now if we started off with 10 grams of the hydrated salt and 5.95 grams are what's left, that means the difference between these two values must be due to the water of crystallization that has been lost. So 10.0 minus 5.95 equals 4.05 grams. So that's the mass of water that has been lost. The next thing we do is convert these masses to moles. So it's going to be 5.95 over the RFM, which is 238, and that equals 0.025. Do the same thing with the water, 4.05 over 18 this time, and that's going to be 0.225. So now it's a case of dividing through by the smallest which is the 0.025, and that's a ratio of 1 to 9. So 9 is the value of X. Now on to C. So we've got our potassium dichromate, which is heated strongly. So there's a thermal decomposition reaction, the breaking down using heat. And we have to calculate the loss in mass when it's heated. Well, if we look over to the right hand side, we see that oxygen gas is one of the products. That gas is going to be released. So these solids will still be in the container, but because the oxygen is released, that means the mass will decrease. So you have to work out the mass of oxygen to answer this question. So the first thing we've got to do is work out the number of moles of the potassium dichromate. Well, the mass has been given, so 1.47 over the RFM, which is 294. That works out to be 0.05 moles. So that is for the potassium dichromate. Now if we look at the oxygen, we see that it's a 4 to 3 ratio. So what we do then is divide this by 4, it converts it into 1, and then multiply it by 3. So over here then it's going to be 0.005 divided by 4 multiplied by 3. And that works out to be 0.00375 moles of O2, of oxygen. So that's the moles lost. Well, this can now be converted to a mass. So it's going to be the number of moles times the RFM of oxygen O2, which is 32. And that's 0.12 grams.